Hello and welcome to this lesson. As it says there, the topic that you're starting here is the Earth and Space topic, and the title for this lesson is Ideas and Evidence about the Solar System. How did we get to understand the solar system as we currently do? I am Mr. Firth. First thing, you're going to need a pen and you're going to need some paper. You will need to be making notes and working through some things on this. You're not just sitting there for the next half an hour watching a video. Okay, so let's get our brains thinking time. There's two questions there. You've got starter A and starter B. Have a read of them, have a think, and I'll come back to you in a few seconds and I'll share my thoughts if you want to freeze it and have a think. Here we go. So, starter A. People used to think the Earth was flat. Understandable once upon a time, I suppose, because people didn't really travel very far. You don't need to go back too far, 400 or 500 years, and people wouldn't have even left the village in which they lived. So their section of the world on which they lived was very limited. It was only as people started traveling further that people started asking questions about the shape of the planet that we actually live on. Can you believe there are still people out there in the Flat Earth Society who will still stubbornly maintain that we live on a flat planet? But never mind, it's up to them, I suppose. Starter B. How has technology helped us to study and understand the universe? I'm sure you've got loads of thoughts on that already, and that is largely what we're going to be thinking about through this lesson. So we'll get onto that and we'll go through loads of ideas on that one going forward. Look at that picture there. Beautiful, isn't it? So that is classic photograph, Earth rising over the moon, taken by the NASA astronaut Bill Anders on the Apollo 8 mission back there in 1968. It looks quite round to me, but as I said, people are more than welcome if they wish to believe that we never went to the moon, that these pictures have obviously all been made up. But anyway, never mind. So, what are we going to go through this lesson? Well, it is work in progress. Bit of a building site, really. What is the building site? Well, the building site is your brain, boys and girls. And we need to get the following things in there so that you've got a good understanding of them through the rest of this lesson. So the first objective we will look at, again, describe how our understanding of the solar system and the universe has changed over time from those early days where people thought we lived on a flat planet to the understanding of the universe that we have today. How do we investigate the solar system? How have our methods of investigating beyond our planet changed over time? And then thirdly, we'll get on to understanding difficulties involved in space exploration. How might we overcome those difficulties as we develop the technology to explore space further? So that's our objectives. That's the work in progress, boys and girls. Hope you're ready to roll your sleeves up and get stuck into it. Right, this is the first objective. As I mentioned, you might want to make quick notes as we go through this, maybe freeze at the end and jot down the key points. So here we go. We're going to start way back with this guy, Ptolemy. Again, as it says, he was a Greek mathematician and astronomer, and he lived 2,000 years ago. How he understood the Earth and its place in the universe, as they saw it then, was what we called the geocentric model. Geo meaning Earth and centric, obviously at the middle. So geocentric. Back then, we believed, or they believed, that the Earth was the center of God's creation. Religion and superstition governed a lot about how people understood the world around them, and that clearly placed the Earth at the center of everything. Everything else just went around it. So that was the early geocentric model. We need to jump forward to this gentleman here, Copernicus, Nicholas Copernicus, a Renaissance-era mathematician and astronomer, lived around 500 years ago. The Renaissance, a massively important time in human intelligence or development of that in terms of rediscovering and developing our understanding of the world around us in a more scientific way. A really important era, that one, for mankind. And again, Copernicus viewed things differently. He challenged the old view held by the church, and again, he had the heliocentric model. Now, helio relates to the sun, helios, hence heliocentric, again, meaning that the sun is at the center of the solar system and the universe as people understood it then. So, make a note. What are the similarities and the differences between their ideas? There are some things that they've got the same, but there are clearly fundamental differences. So make a quick note before you move on to the next slide. Okay, We can't discuss the Renaissance and great Renaissance characters without mentioning this guy, so famous that he's even had famous songs written about him. I won't embarrass myself by trying to sing any of them. He is, of course, Galileo. Thankfully, we abbreviate his name to Galileo because there's his full title, Galileo di Vincenzo Bonolti di Galilei. That's a bit of a mouthful, but as it says there, he was an enlightened guy for the times, and clearly he deserves that title, the father of observational astronomy. Now, he used a very basic early telescope. Lenses that we need for telescopes had only just been invented back then, so obviously you needed lenses before you can start to make telescopes. Now, using those early telescopes, he made a monumental discovery. There it is. He observed through his telescope Jupiter, and more importantly, he observed that around Jupiter were these smaller bodies orbiting Jupiter. Now, think about it. How did that challenge the geocentric model at that time? Well, it was a massive challenge, really. The church would inform you that everything orbited the Earth. Galileo came along and said, well, actually, if you have a look at Jupiter, I can clearly show you with my new telescope that we've got these smaller moons that orbit Jupiter, not the Earth. So, you're wrong. Church weren't too pleased about that. They actually put him under house arrest for a good period of time to thank him for that monumental scientific discovery. Of course, we have now observed those four moons of Jupiter in great detail. A nice image there to show you what they actually look like. Right, so moving forward in time a little bit, we get to the modern model that we have currently of the solar system. So have a look at that image there. We can see the four inner planets orbiting the sun, not to scale, of course. And we can also see the asteroid belt there, and it shows us the orbital planes of the outer planets also. Have a look at this one then. Again, little animation, not to scale, obviously, that shows the 9 planets. Very nicely, this slide allows Pluto to still be a planet. Some people very cruelly won't let it be a planet anymore. They've downgraded it to a dwarf planet. A bit unfair, that, if you ask me, but never mind. Okay, now, as the question says, are the orbits circular? You see, this is different, isn't it, this picture, to the model that Copernicus had with circular orbits. Would we call the shape of that orbit? I'll give you a clue. The first letter, E. I'll talk you through the rest of it, see how quickly you can get it. Double L, I, P, T, I, C. I'm sure you've got it by now. A, L. They are, of course, elliptical orbits. Another nice diagram there showing you that model, the modern model with the elliptical orbits there, with the planets in there. We have this guy to thank for this one, Johannes Kepler, German astronomer and mathematician, another very clever guy for his time. But it was his laws of planetary motion that allowed us to understand the true nature of the orbit being elliptical. Just one more thing before I finish on this slide. If you want to ever be able to remember the 9 planets, if you're not sure of this one, the best way to remember it is the following. My very easy method just speeds up naming planets. There we go. And that one, of course, still allows Pluto to be a planet. Go on, Pluto. This gentleman needs no introduction from me whatsoever. As it says there, widely recognized as one of the most influential scientists of all time. We still use a lot of his theories today, and certainly in year 10, his laws of motion are things that we expect you to understand in a lot of detail. So he very famously produced this book in his lifetime, Principia, and again, the Principia states his laws of motion, as I've mentioned, but again, it also brought in his laws of gravitation. Newton, as some students have told me in the past, did not invent gravity. Think about it, if he did, people would have just been floating around prior to when he was alive. He was the first person to theorize gravity and come up with it and explain it as a concept that we could understand and quantify. He built upon Kepler's laws of planetary motion, as mentioned from the previous slide. And again, that's where he came up with one of his most famous quotes. If I've seen a little further, it's because I've been standing on the shoulders of giants. What Isaac's doing there is he's saying thank you to the people that went before him. He's acknowledging that without their discoveries, he wouldn't have been able to make the giant leaps that he made back then. Another famous quote that he made, not a lot of people are aware of this one, he also said, without it, gravity is just gravy. Take a minute to think about it. Of course, other brands of granulated gravy products are available. Right, as happens in any normal lesson in a classroom, this is the bit where a teacher shuts up and you lot get on with some work. So what I'd like you to do is make a sketch very quickly, as you can see there, of the Ptolemy's model, the geocentric, and the modern heliocentric model. And then what you're going to do is underneath or with those diagrams, you are going to sort those statements as to which model that they belong to. You could do that as a table if you wish, or, as I'm suggesting here, you could do it as a Venn diagram. It's entirely up to you. I don't mind, so long as you've got those diagrams and, again, you've done your best to sort those statements into the correct place. So here's the slide again. Off you go. I'll come to the answers in 3, 2, and 1. So there we go. For the old geocentric model, of course, the Earth was in the centre, as they thought then. The sun moved around the Earth, and that's what caused day and night. When it was on the other side of the Earth, it was night. When it was on the same side of the Earth as you were, it was day. That's how they saw it. And if you think about it, it sounded perfectly reasonable. Other planets orbit the Earth, as we said. Everything orbited the Earth, as they thought back in those days. And the sun, the moon, and the planets, the orbits were circular. They moved in perfect circles around the Earth in the middle. Evidence was gathered then, of course. It's the only method they had. Lenses hadn't been invented. There were no telescopes. So they just looked. It's what they saw with their eye when they looked up into space at night. New model. Sun, of course, is in the middle, heliocentric. The Earth orbits around the sun, of course. The Earth spins on its axis. Of course, that's what gives us night and day, as we now know. The moon and the planets, as Kepler helped us to understand, they moved in elliptical orbits. They weren't perfectly spherical. And evidence was gathered increasingly using telescopes. And so that evidence got clearer as we developed better telescopes to look into the sky. Both models, of course, the moon orbits around the Earth. So that one there is in both of them. Second objective time. So how I'd like this one to work, I'm going to show you a bit of information over the next 2 slides, and then I'll tell you what I want you to do with that information. So have a think about those pictures there. You might know something about some of them already. I'll give you a countdown and I'll tell you a bit more about each one. 3, 2, 1. Well, we've got a NASA space shuttle there. Lots of space shuttle missions into space, obviously, hence the name of the space shuttle. And again, you might want to find out a bit more about individual ones. Next to that, we've got the Hubble telescope. Again, a great step forward, allowing us to see greater detail, much more clarity in the images that we now see of more objects distant in space. Have a look at some of them. They really are fantastic. We've got Galileo's telescope. Again, great leap forward in terms of allowing us to see more detail and start asking those questions which brought us to our current understanding. We get more famous than that one. I'll say no more. Stargazing. We've done that since the dawn of time, looking up at the stars, wondering about them. Why do they have the patterns that they have? Coming up with ideas of constellations, linking them together. We've always been curious, we've always wondered, and now, of course, we're at that stage where we can actually go out and start finding out. Sputnik, what was that? I'll let you find out. What role did that play in space exploration? Mars Curiosity rover, again, it's obvious where that one is. Find out more about it. How have we found out what we now know about the surface of Mars? Jodrell Bank Radio Telescope. Doesn't look like a telescope in the traditional sense. It's not long, thin, and tubular, but it is a telescope still nonetheless. Cassini probe there. Now, the Cassini probe should be clear from the picture. Was sent out there to study in more detail Saturn, the moons of Saturn, and the ring structure around Saturn. Voyager probe is now, it's been going out there, it's been going for a good 50 years or so, I think, and again, it's now beyond the outer parts of our solar system in what we now call the Kuiper Belt, beyond Pluto, the Kuiper Belt, where we believe comets come from. Comets, of course, sweeping in towards the sun with massively elliptical orbits, sometimes coming close to the orbits of some of the planets. So, some more there. Have a quick look. Are there any that you know about? I'll give you a countdown and I'll let you know what each one is. 3, 2, and 1. Right, We've got a very advanced telescope there. That's a light telescope. Again, that's looking at the visible part of the spectrum to tell us about stars in space. And that's a Keck telescope in Hawaii. We've got a Soyuz manned spacecraft there, again, part of the Russian space program, or Soviet space program, should I probably say. There we've got a Galileo probe to Jupiter. Clearly, hopefully you should understand why that probe was named after Galileo. We've got there a Venera probe, Venera 4, that one. Again, that was the first probe to land on the surface of Venus. If you do a bit of research and find out what it's like on the surface of Venus, you'll understand why getting something there, and actually it sent pictures back, you'll understand why that was an amazing achievement, again, by the Soviets as part of the space race back there in that old Cold War. What have we got here? Again, the New Horizons mission to Pluto. That's a relatively recent one, that. And again, we've now got that advanced in terms of technology and space exploration. We can take clear images of these distant objects in our solar system. Very famous guy there. If you don't know who he is, you should do. Yuri Gagarin, first human to go into space. Cassini spacecraft, again, around Saturn, but as part of that mission, it released the Huygens probe to the surface of Titan. And again, we've got really good images from that Cassini probe and the Huygens probe there, out there to have a look at if you fancy finding more out about it. This one here represented a really big jump in terms of our ability to do things. To put a probe onto a comet whizzing round our sun in our solar system is a massive achievement in terms of the technology required to enable us to do that. Again, if you want to find out more, the Rosetta comet landing, there are pictures out there on that one, really interesting. I'll put the last one in there for Mr. C to boldly go where no man has gone before, of course. Star Trek taking us forward, but it's important to remember a lot of science fiction does eventually end up becoming science fact. Who knows, that tricorder that I brought on the internet might actually work one day, although I have mastered the Vulcan death grip. Okay, so again, it's time for you to do a bit. Now, again, you might want to put a lot into this. You might not want to put quite as much in. I'd certainly like to see you attempt to put in the earlier information from this lesson onto a timeline. Now, the way a timeline works, obviously, it shows you a progression of something through time. I've given you a diagram of one there. That's the way I've done it. You don't have to do it the same. It could be a long, straight, linear one on a piece of paper. You might need to stick a couple of sheets together, possibly. Again, as I've done, try and put on the scale. And again, you'll notice in some places where I have put the dashed lines, and again, those dashed lines are showing that there is a change in the scale. So I've got 1,500 years worth of time here. And again, the next part goes up in hundreds of years until here at 1900 to 1950 again, because there was more things happening at this time. And again, certainly this period of time here, hell of a lot more happening. So therefore, your scale might have to be different for different periods in time. So from the previous two slides, from the things that we thought about in terms of the geocentric model and the heliocentric model, I'd like you to have a go at constructing a timeline. As I said, this could be a very short piece of work. You could, if you wish to go to town, produce something monumental. And if you do go that far, please share it with us. I'm pretty sure that we can sort something out for those people that have really gone above and beyond on this one. So, final objective, difficulties involved in space exploration. How are we trying to overcome them? Would you, given the chance, volunteer to go on the first manned mission to Mars? It's possible that in your lifetime somebody will. If you was asked, would you go? If the answer was yes, you need to consider the following. What dangers would you and the crew be exposed to on the mission? Can we rely on the technology to actually get you there? Is it good enough? Would you take the chance? How much is it going to cost? Is it worth it? Again, have a quick think about them. You might want to jot down your thoughts. I'll share mine with you in 3, 2, and 1. In terms of dangers, well, how long have you got? First of all, you've got to get in a rocket, which is basically a massive big missile, isn't it, at the end of the day, with a load of explosive material strapped to you, and you've got to get off the surface of the planet. That in itself is a risky business. They don't call it rocket science for nothing. Then, once you're beyond the protective layers of our planet, beyond its magnetic field, beyond the atmosphere, you're exposed to all kinds of radiation from the sun, again, at a much higher level than you would be normally. You've got to factor in the time that it's going to take you to get there, at least a year. And when you're there, you've got to stick around for at least a couple of years or thereabouts. Then you've got a year back. Again, all of that time, you've got to assume that that technology that you're relying on is going to keep working in a situation where it's not properly being tested. It's a massive leap of faith for anybody that's going to make that commitment. How much would it cost? Is it worth it? Depends how you think about this one, what your outlook is. If it was a global effort and in some way it enabled mankind to work together on one project, well, surely that's got to be worth any cost, hasn't it? I would argue so anyway. Is it worth it? Well, I don't know. In terms of, well, we can't quantify that until we've actually been there. We've got a lot of problems to sort out on our own planet, obviously, but certainly something of this nature may help us to put things into more perspective. In terms of being famous, well, you all know who Neil Armstrong is, so certainly you'd be more famous than your average attendant on your average goggle box. I just wanted to share this one with you in terms of advances in technology. Now, this is cutting edge stuff here. You may well have heard of SpaceX. It's a company, private company that's launching things into space at the moment. Now, they have made massive improvements in technology. Now, if you have a look at that fact there, the old space shuttle, it used to cost £54,000 per kilogram of material launched into space. Now, a kilogram, if you want a reference, you've got a bag of sugar there. You've all seen one of them. So imagine how many bags of sugar there are in your average capsule going into space. It's a big cost. Now, SpaceX, look at that. That's phenomenal. They have currently reduced that cost to $2,720 dollars per kilogram. So again, that rocket you can see there is actually a Falcon Heavy. I think that's what the FH stands for. One of the larger ones. You can see the booster rockets on the side. Here's one launching. Now, where SpaceX is clever, clearly all of that, once it's gone up, old rocket technology was use it once and that was it. It was wasted. Check out what they've done at SpaceX. Now, those boosters that we used for the initial stages of the launch, once they've been ejected, they can then reignite and fire their own boosters. And as you can see there, it's pretty amazing, really. They land, they use them again. All of these things help to reduce the cost. The cheaper that cost gets, the more things we can get into space, which makes that exploration to places like Mars more possible. Have a read through that then. As it states, we haven't been back to the moon since 1972. There was more than one visit by NASA astronauts to the moon, but certainly the last one was 72. Since then, other than, of course, occupying things like space stations in Earth orbit, we've not been any further than that. As hopefully you can get an idea from previous slides, we've had loads and loads of probes out there exploring for us, sending back loads of really key information, but certainly no human has ventured any further than the moon as we currently stand. So, the question there states, many people think that astronauts should be sent to Mars. Others disagree. What do you think? Your opinion matters, boys and girls. What are your thoughts on that? And that's how we're going to look at things from the rest of this lesson in terms of scientific argument. Scientists have to make reasons for their ideas and their theories. Other scientists will disagree with them. And again, by that process of argument, counter-argument, hopefully we come up with an idea that works, that people agree on, and those theories become accepted as fact. So let's have a look at a scientific argument. Here we go. So we've got two people there, and we need to open up with a key point. So key point comes. Space travel is dangerous and astronauts will have to be protected against radiation and the effects of weightlessness. This gentleman's there backing that up. Astronauts take a long time to recover after 6 months on the International Space Station. So, you know, it's a bit of a dodgy thing. Well, actually, this person thinks there are plenty of people. There's loads of people out there willing to risk that journey. And I know for a fact that some nations have already started the training of astronauts for that journey. But Can we afford to send astronauts to Mars? Surely for the cost of just sending a few astronauts, we can send loads of probes. That's just as good, isn't it? Don't you think? Well, actually, astronauts can make decisions while they're there. Okay, if they spot things, they can make intuitive links to things, which you could argue computers can't. So actually, I think space exploration is developing rapidly, and therefore within our lifetime, we may develop the technology to reduce the risk and the cost of going to Mars. She might have a point, and she's certainly got a very deep voice. Okay, it's your turn again. So again, a bit of literacy and science here for you. Again, it's the same argument. There are some statements coming up, and again, I want you to arrange those statements into an argument in favour of sending humans to explore Mars. So here are the statements. Here you go. Have a think about them. Again, you might want to use some conjunctions to link those statements together. Again, a conjunction used in sentences to join or to link things together to make the flow of that sentence clearer. So again, if you want to use some conjunctions on top to link those, then that's fine. Again, you might want to, as I did previously, use different colours there, okay, for the different parts of the argument. Again, if you want a bit of a help, I'm going to give you what the key point is in 3, 2, and 1. So answers time, and there we go. Key point: other planets can be explored by sending humans or space probes. Evidence for that key point: astronauts visited the moon. Again, they made many scientific observations and brought back rock samples from the moon. Objection: many people say it will be too expensive to send astronauts. It does cost a lot more to send people than to send space probes. Counter argument: however, the public are more interested in human stories. People possibly would be more willing to allow their money, their taxes, to be spent sending astronauts rather than sending space probes. Conclusion: sending astronauts would be the best. Now, that's the way I've linked them together. Again, hopefully you've got something similar. If you want more, try this one. The moon landings are fake. My mate read something about it on Facebook. Bit controversial. Oh dear, this one might take a while. Again, would you object to that argument? As I've said, your opinion is your opinion. If you want to agree with it, that's fine. But can you offer any evidence to support that argument that the landings were actually fake? If you object, what would your counter argument be? What evidence would you give them? Again, if you want to do some research on this, there's a load of stuff, as you can imagine, out there that you can use to get your own opinion. It's important. How would you offer possible objections to that argument? I've clearly made my mind up. There's a very happy-looking science teacher there holding on to something. Let's have a look at a little bit more closely what that is he's holding. So again, if we zoom in, you'll notice there, as it says in the middle, that is lunar sample number 227. At science teacher parties, we get the chance to have a look at things like this. Clearly, while I'm there with a big grin on my face, he's thinking, get a move on, mate. Can you hurry up? I need to have a look. Thank you very much. And finally, so thank you very much for sticking through to the end. Hopefully it's helped to give you an idea of our understanding of space currently, and more importantly, how we got to that understanding. Again, just to prove that you can't always trust things that you see on the internet. If ever you do want to know what it is like to travel through space at the speed of light, you're going to need to ask that dog. Thank you very much, boys and girls. I'll see you with another lesson shortly.